Welcome back everyone. In this lecture we will actually classify all the irreducible root system using the respective Dinkin diagrams. So let us start. So let us fix some notations before actually proceeding further. Let us take phi to be a root system sitting inside the Euclidean space capital E. So this is the Euclidean space. And phi is the root system. So we already seen that any root system can be written as direct sum of irreducible root system. So classifying any finite root system will boil down to classifying finite irreducible root system. So for that reason we just assume this phi is irreducible. Okay, so what is the definition of irreducible? So phi cannot be written as disjoint union of phi 1 and phi 2 such that both of them are orthogonal to each other. So recall, so here is the definition. So phi is irreducible if we write phi as disjoint union of phi 1 phi 2. So then there exists alpha in phi 1 and beta in phi 2 such that the inner product alpha beta is non-zero. So we also defined a Coxeter graph associated with this root system phi. So recall what is Coxeter graph of this phi. So it is actually has vertices as the pi system, sorry, the base that is chosen in phi. So that is also we need to fix. Let us say pi is a fixed base inside phi. So this is a base of phi. So what we do, we list all the elements of pi to be alpha 1 etc. alpha n. So this is order that we actually choose. So now what is Coxeter graph of phi? So it has vertices as pi. So vertices of this graph, let us call it g of pi. So this is the graph. So vertices of g of pi are nothing but alpha 1 etc. alpha n. So then you draw edge from I to j. Okay. So now we draw like we draw exactly 4 times the inner product. Okay, maybe I will tell in terms of the Cartan numbers. So recall the Cartan number alpha comma beta, the angle alpha comma beta is nothing but twice alpha beta divided by beta beta. So in particularly we draw, so these Cartan numbers are integers we know, and we take this alpha beta times beta alpha number of edges we draw between alpha I beta. Okay, let me start with I and j. So these numbers should be non-positive integers for any alpha beta coming from pi. Okay. So in particularly if we fix I and j, so start with ij, start with alpha I alpha j in pi such that I not equal to j. So then draw exactly alpha I times alpha j, this Cartan number times alpha j alpha I number of edges between the vertices alpha I and alpha j. So this is going to give us a graph which has multiple edges now. Okay. So, this graph is called Coxeter graph. So, where the vertices are this the pi system, sorry, the base that we have chosen alpha 1 etc., alpha L, and you draw between alpha I and alpha j exactly this many number of alpha I alpha j times alpha j alpha I number of edges. So, note that this number product of these Cartan numbers. So, it has to be exactly either 0, 1, 2 or 3. So, in particularly the number of edges that you draw between I and j can be at most 3. So, now what is Dinkin diagram? So, Dinkin diagram, you take Coxeter graph. So, take Coxeter graph of phi. So, note that the Coxeter graph of phi actually indeed does not see the lengths of the roots that we are actually talking about, because we are only drawing these many number of edges between alpha I and alpha j roots or the vertices. So, it does not really say which one is long root and which one is short root if you have two root lengths inside your phi. So, to avoid this confusion, we already seen that any given irreducible root system there could be at most 2 root lengths, and there are examples like B2 that has 2 root lengths. Okay. So, in particularly we need to specify if you want to recover completely your phi from the Dinkin diagram, you have to specify exactly which root is long and which root is short. So, suppose if you have alpha I and alpha j and you want to compare. So, let us say there is an edge between them. Okay. If there is no edge, then we can't actually say, but if there is an edge between them, let us say there are some edges. Okay. So, then you put an arrow from alpha I to alpha j if alpha j is short root. So, this arrow always points towards the shortest root, point towards the shortest root among alpha and alpha j. So, this way you get what is called directed graph. So, that is what you call it Dinkin diagram. We already seen that how to recover the root system from the Dinkin diagram. Okay. So, now what we are going to do? We are going to, so in particularly we can recover the Cartan matrix from the Dinkin diagram. In particularly using Cartan matrix we can recover entire root system, that is what we have seen in the last class. So, now what we are going to do? We are going to actually classify the irreducible root systems using their Dinkin diagrams. So, I already specified in the last class. So, what are all the possible Dinkin diagrams of irreducible root system? So, that is listed here. So, if you take for example phi to be irreducible root system of rank L, then its Dinkin diagram must be one of the following, either type A, type B, type C. So, type B and C they have same Coxeter graphs, but once you decide the arrow then they define two different types of root system, and type D and type E, where E you have three different root system E6, E7, E8 and F4 and G2. So, these are all the possible Dinkin diagrams that you get. So, I also claimed we will be seeing soon that for each Dinkin diagram that is listed here, we will be able to construct the root system very explicitly. So, that maybe I will do it in the next class. Okay. So, now look at all these possible diagrams. You can easily see that except this B and C, the Coxeter graph actually uniquely determines the Dinkin diagram of all other types of root systems. So, only in B and C we are not able to decide from the Coxeter graph which one is B and which one is C, but all other types you can see that, because for example, in type A and then D and E there are no arrows. So, they are called simply laced. Okay. So, these types A, D and E, because they all have all the roots in these types have same length. So, they are called simply laced types. All other types are called non simply laced types. Because they are simply laced, there is no arrow. So, in particularly they are uniquely determined from its Coxeter graph. Coxeter graph and Dinghen diagrams are same. But in types B and C, you can see the arrow determines which type it is. And if you go to type F and G, so basically the arrows do not matter, because if you even reverse the arrow, you get the same diagram. So, basically that is because F4 dual is isomorphic to F4, and as well as G2 dual is isomorphic to G2. So, the dual is the only thing that is going to create problem, but they are all self dual. So, there is no difference. So, now what we are going to do, we are going to prove that these are all the only Dinghen diagrams are possible. But for that purpose, let us first observe something about what is called this admissible roots. Okay. So, first we will make a theorem that is about admissible set of vectors, and then later using this information about admissible set of vectors, we will actually apply directly that information to the set of this vectors that comes from the base. So, then we will conclude our theorem. So, okay. So, what is admissible subset of capital E? So, let us first define. So, it is naturally motivated from the base only. So, recall, so what are all the properties of base? So, this pi is a base of this root system phi. So, since pi is actually base, so in particularly if I take this pi to be just alpha 1 etc. alpha L. So, one important property of this pi is nothing but if you take the inner product between alpha I and alpha j, that must be always negative. That means, the angle between alpha I and alpha j must be obtuse for all I not equal to j. So, this is one important property, and the second property is if we take this Cartan numbers alpha I times alpha j and alpha j alpha I. So, these must be having value 0, 1, 2, 3. So, this is again very strong condition that comes from the Cauchy-Squartz inequality. So, we take, so now you can see that these Cartan numbers indeed does not depend upon the inner product that we have actually chosen. For example, if you scale the inner product by some positive real number, so then this Cartan number does not change. So, only the Cartan numbers matters for us, because the Cartan numbers constitutes this Cartan matrix. Okay, Cartan matrix you can actually recover everything about the root system. So, scaling this inner product actually does not harm us anyway. So, in particularly what we can do, we can take pi and then you can normalize all the vectors in pi. Okay. So, that also kind of does not change the properties of these roots. So, in particularly by normalizing them, we can assume them to be unit vectors. Okay. So, that is what admissible set all about. Okay. So, basically they are motivated from the base. So, let us define admissible set, let us work with admissible set, then later we will actually specialize to base. Okay. What is an admissible set? So, it is a subset of E. So, let us say it is collection of some n vectors. So, E is the Euclidean space. So, then what we say, the dimension of E is L, let us say. So, the dimension of E is L. So, L could be some arbitrary dimension. So, you call this n number of vectors from capital E. So, they are actually, they is said to be admissible, more or less they satisfies all the properties of base elements, said to be admissible if it satisfies the following conditions. The following conditions. So, what they are? The very first condition. So, they must be linearly independent. Okay. So, all epsilon i's are linearly independent, and we also assume them to be unit vectors, independent unit vectors. And then the second condition, whenever you take inner product between them, that must be always non-positive for all I not equal to j. So, since they are all unit vectors, you can see that epsilon I that must be 1 for all I. So, the third condition, if we take this product of this Cartan numbers, so in this case it will be just 4 times epsilon I inner product with epsilon j square, because the inner product epsilon I and epsilon j must be 1. So, this must be again integer and it can take value between 0 to 3, 0, 1, 2, 3. So, if your epsilon i's coming from capital E satisfies these 3 properties, then you call them admissible elements. Okay. So, what we are going to do? We are going to actually understand these admissible elements in terms of what we call the Coxeter graph of these admissible elements. Again, you can define this graph. So, again we call it Coxeter graph of A. So, note that this we denoted by G of A. So, if you think about Dinkin diagram, so except in type B and C, all other Dinkin diagrams are uniquely determined by their respective Coxeter graphs. So, it is enough to actually classify Coxeter graphs. Okay. Then later you can just decide where to put arrow, but there are only choices will are limited. Then you can see that only B and C will pop up, except all other types will be uniquely determined by Coxeter graphs. Okay. So, what is Coxeter graph of capital A? So, which we denoted by G of A. So, the vertices of G of A, you take it to be capital A. So, vertices of G of A, all the elements of this capital A. So, which is exactly epsilon 1 etcetera epsilon n. So, now what you want to do? You take 2 epsilon I and epsilon j, and then what we are going to do, the edges we have to say what are they. So, you take I not equal to j, consider epsilon I and epsilon j. So, you basically draw some number of edges where you draw like 4 times epsilon I epsilon j square number of edges between epsilon I and epsilon j. Note that since this 4 times epsilon I minus epsilon j square, that is either 0, 1, 2 or 3. So, maximum 3 edges are possible between these two. Okay. So, this is the Coxeter graph of capital A. So, now what we are going to prove? So, for any admissible set, Coxeter graph of that admissible set must be actually has very specific choices. Okay. So, it cannot be just arbitrary. So, of course, we are interested in the connected Coxeter graph. Okay. So, we will just focus on Coxeter graph of A for which G of A for which this Coxeter graph of A is connected. Okay. So, what we are interested in, we are only interested in admissible sets capital A for which G of A is connected. Okay. So, that is somewhat underlying assumption. Okay. So, let us make some observation about admissible sets that will actually help us concluding what we want. So, note that any subset of an admissible set must be admissible. So, that is easy to see. Any subset of an admissible set must be admissible. So, you can easily see that or readily see that all the properties of subset must satisfy all these three properties. So, there are no options. So, in particularly if we take this graph of G, graph of this capital A, G of A. So, then what you can do, you can ignore some vertices and then take subgraph corresponding to that, that will be again graph of some admissible set. Okay. So, discarding some vertices is again going to give us Coxeter graph of some admissible set. Okay. So, what is second property? So, it is about the number of pair of vertices in G of A. So, that has some edge between them. Okay. So, what one can prove, the number of pairs, again it is counted as unordered pairs, because all we are interested in whether given given epsilon I and epsilon j or given I j, whether there is an edge between them or not. So, if I j has edge, then j I has edge. So, you count it as unordered pair. So, given these pairs of vertices, so you count the number of pairs of vertices in G of A. So, that is connected by at least one edge. So, this number we are going to say this is going to be strictly less than n. Okay. So, this is very important property. So, basically it says, so the graph, if you consider graph of this admissible set that cannot contain cycle. So, that is immediate from this observation. So, then it must be actually a tree. Okay. But again, like now we are talking about graph that having multiple edges. Okay. But you can take again tree, the definition of tree as this kind of general graph that does not have any cycle. Okay. Again, okay, maybe like you can consider the simple graph that actually their underlying simple graph of G of A, that is tree. Okay. So, that is what we conclude. Okay. How one proves about this? Again, this can be proved by understanding the geometry of this admissible vectors. Okay. So, because there are lots of constraints that you can see geometrically there in the definition. So, for example, they form obtuse angle, and then whenever you compute this product of quarter numbers, that must be at most 3. So, all these conditions actually kind of puts lots of restrictions. So, let us see how one can prove this. So, what we do, we take this epsilon, so which is summation epsilon I range from 1 to n. So, this is definitely a non-zero element, as epsilon i's they are linearly independent. So, now what we do, we just simply compute epsilon. So, then you can see that immediately that inner product has all the information about the pairs I j such that epsilon I epsilon j non-zero. Okay. So, just compute this epsilon. So, since this must be positive because epsilon non-zero, then you can see that since epsilon I is 1. So, this is exactly equal to n plus twice summation I less than j epsilon I comma epsilon j. So, where this I j varies over a pair of indices for which epsilon I epsilon j non-zero. So, this is I j such that you can see that epsilon I epsilon j is non-zero. Otherwise, there is no contribution of that inner product. So, this is just immediate from the definition. Now, what is about this twice epsilon I epsilon j? So, let us try to see what it is. So, note that 4 times epsilon I epsilon j square. So, this must be either 1, 2, 3 because epsilon I epsilon j is non-zero, epsilon I epsilon j being non-zero for this pair. So, that implies, so this has to be either 1, 2 or 3. So, then that implies when you compute this twice epsilon I epsilon j. So, that must be at most minus 1. Okay. So, because this has to be a negative integer and it has to be non-zero. So, that implies that this has to be at most minus 1. So, then you can see that okay. So, we have not actually assumed anything about this twice epsilon I epsilon j, because all we have assumed about only the 4 times epsilon I epsilon j square. But anyway, this inequality is clear, that is just because this number can take either 1, 2, 3. So, this square root has to be less than or equal to minus 1. So, that is clear. So, now what you can conclude from this, if you go back to the number that we are interested, call this is some m. So, then you can see that from this inequality, so this minus twice summation epsilon I epsilon j, again I less than j epsilon I epsilon j non-zero, this term can be at most n. But this term you can see that has to be bigger than m, because this twice epsilon I epsilon j is less than or equal to minus 1. So, that means minus twice epsilon j is greater than or equal to 1. So, for each pair I j such that epsilon I epsilon j non-zero, you get this number is greater than or equal to 1. So, that means this entire sum is greater than or equal to the m that we want. So, that proves that m is actually at most n minus 1. So, that is a very, very important observation. So, if you are in a graph, even if multiple edges are there, so then you can see that okay, if you remove the edges that are actually, if you remove multiple edges and make it one edge, so then you can see that from that multiple edges graph you can get what is called simple graph. So, simple graph is a graph in which either you have edge between given two vertex or not. Okay. So, no multiple edges are allowed. But even for simple graph you can see that if you have simple graph and then the number of edges are at most n minus 1, where n is the number of vertices, then that graph must be actually tree. Okay. So, that means what we can prove even here in this case, g of a must cannot contain any cycle. So, contains no cycle. So, this is what one can prove. Okay. So, how one prove this? A cycle, if you have cycle, let us say C inside this g of a. So, then you can just focus on this cycle. Okay. This cycle is going to be something like this. Again note that, so there could be multiple edges also between them. Okay. So, when what I mean by cycle, so at least two vertices should be involved, and then you start with one vertex and then go around and then come back to that vertex from some other vertex other than this one. Okay. So, that is what we mean by cycle. So, we don't want to call this kind of things as cycle. Okay, going here and coming back here. So, cycle by definition for us it should have at least 3 vertices. Okay, that is what our definition. So, cycle should have at least 3 vertices. So, that is our convention. Okay. Now, if you have a cycle something like this, then what you can do, you can restrict to that particular set of vertices that are there inside C. But we have seen that any subset of an admissible set must be admissible, In particularly if you restrict to the vertices of C. So, this also must be admissible. Okay. So, in particularly if you restrict to this subgraph, so then the number of pairs for which there is at least one edge between them, okay, the number of pairs of vertices inside that C connected by at least one edge. So, that can be at most n, that is what we have seen. Okay. So, let us say this cycle has exactly k number of vertices. So, then this number of pairs must be at most k, but you can see that if you start counting the edges, okay, it should have at least k edges. Okay. For example, here there are 5 vertices. So, you can see that there should be at least 5 edges in this. So, that leads to contradiction. Okay. So, that means G of A cannot contain any cycle. So, this is a very important observation. So, now what we are going to prove, so that means G of A can be some kind of tree, okay, like it could be something like this. But what we are going to say, we will again have more restrictions, and so that way we will limit to only the possibilities that we saw earlier. Okay. So, maybe like I will prove this one more observation and then stop, because we are running out of time. So, what we are going to say, so let us look at some vertex where some branches are there. So, that means, so given this vertex there are some edges that actually kind of pops out from this vertex. So, call this vertex epsilon, and then you have this eta 1, eta 2 and so on. Eta k is actually just adjacent to this epsilon, and of course, there could be some multiple edges. Okay. So, there is no restriction that we have so far. So, at most 3 edges can be there between epsilon and eta I. So, note that number of edges between this eta I and epsilon. So, that could be, because we have assumed there is at least one edge. So, this could be at most 3, okay, and at least 1. So, now let us see what it means in terms of inner product. So, it means the inner product epsilon eta I must be less than 0 for all I 1 to k. Okay. So, now from 3, so 3 says that G of A cannot have any cycle. So, that means any 2 eta I and eta j cannot have a edge between them, because if there is an edge, so then what will happen, if that edge is there, that will make actually triangle. So, that will give you cycle, okay, which we do not want. So, that means eta I, eta j must be orthogonal to each other for all I not equal to j. So, now using this we just try to get more restriction on this epsilon eta i's. So, let us see what it is. It is a very clever idea. So, we will restrict to the subspace that is spanned by this epsilon eta 1 etc. eta k. So, note that all these epsilon eta i's, they are all distinct, and again it is subset of admissible set, it must be linearly independent. So, the dimension of this must be k plus 1. So, the dimension of this space must be k plus 1, and eta i's, they are all orthogonal and they are unit. So, already you have orthonormal subset. So, this eta 1 x eta k, this is orthonormal subset of this subspace. So, now what we can do using this Gram-Smith orthogonalization, you can extend this basis to orthonormal basis for this subspace. So, call this subspace E dash. So, then E dash you can find a basis, call it eta naught, eta 1, etc., eta k. So, this is orthonormal basis. So, this can be done using Gram-Schmidt. So, now note that because this is obtained from extending this eta 1, etc., eta k orthonormal subset. So, epsilon is not in the span of this eta 1, etc., eta k, that implies that the inner product epsilon eta naught must be non-zero. Okay. Not only that, you can write epsilon is equal to summation epsilon eta I where I ranging from 0 to k. So, this is also possible because this eta i's form a orthonormal basis. But epsilon is actually unit vector. So, epsilon is 1. So, that puts lots of restriction. So, in particularly if you compute epsilon, so which is 1. So, you can see that this is exactly equal to summation epsilon eta I square, I range from 0 to k. So, then this means summation epsilon eta I square where I range from 1 to k must be strictly less than 1. So, this is very strong restriction on the squares of this inner products. But how many edges are there? Let us say. So, between epsilon and eta I you have exactly 4 times epsilon eta I square number of edges. So, that is what you have. So, in particularly you can see that this gives lots of restriction on those number of edges. So, summation 4 times epsilon eta I square where I range from 1 to k must be strictly less than 4. So, that means the number of edges all together that originate from this epsilon. Okay. So, that must be at most 3. Okay. So, this is gives lots of restriction. So, basically what we proved that no more than 3 edges can originate at a vertex of G of A. So, that is what we proved. So, this actually kind of puts lots of restriction. For example, you can't have something like this. Okay, this is forbidden completely. And not only that, any more branches. So, if there is a branch, the branch should have only something like this. And again, the multiple edges also cannot be there. So, this is also not allowed, and anything like this is allowed. So, it actually it's easy to list what is allowed using this. Okay. So, let us see one immediate corollary of this and then I will stop. So, one immediate corollary that if you have connected graph G of A of an admissible set capital A that contains a triple H. Okay. So, then you can prove that must be the Coxeter graph of G2. So, this is the only graph. Okay. So, let me draw it properly. So, is the only graph that can be actually G of A of an admissible set A for which that contains a triple H, is the only graph G of A that is connected and contains a triple H. Why? Because if we start with this portion, okay, this is going to be admissible, that is fine. But from this vertex you can't have any branch. Okay, there cannot be any other vertex that is connected with this vertex. So, that is forbidden. Okay. Similarly, from here also you can't have anything that goes out. So, that means you end up only getting these 2 vertices with 3 edges. So, that way we are actually getting lots of restriction. Okay, I will stop here because we are running out of time. So, I will continue with the classification in the next class. Again, this is actually indeed a very big theorem. We need to make some more observation in order to actually conclude what we want. Okay, I will stop here. Thanks.